Welcome to topic 9 about deep learning recurrent neural networks or RNN. So we'll be talking about what RNN or recurrent neural networks are and how do we actually apply them to some applications. First, a quick word about recurrent neural networks. So within the Keras interface itself, it actually has support for three types of RNN architectures. Simple recurrent neural networks, long short-term memory or LSTM in short, and the last one GRU or gated recurrent units. So RNN follows from the idea that we had in CNN, where we take advantage of some local representation in the data itself. That means some local structure in the data that helps us to implement the neural network in two portions. The first portion being some part which actually does feature extraction from the data itself, and the back end there's actually a normal multi-layer perceptron or classifier. So for recurrent neural networks, we have something that does the feature extraction as well. But in this case, the data is not images, but typically it is good for extracting information that has a particular sequence in time. For example, extracting patterns of data that's related to languages. Okay, so for most languages, the sequence of words that we use, they have special meaning. For example, the sentence grandma bites dog and dog bites grandma, three similar words, but because of the sequence of the words, they have totally different meanings. So recurrent neural networks makes use of the sequence of the words. So they have much promise in many natural language processing tasks or NLP tasks. So the basic idea behind the recurrent neural networks is actually shown in the diagram here. So we have an input section, input neurons, and then we have the output neurons, which is a fully connected layer. And then we have a number of hidden layers. But the difference between the hidden layer in a recurrent neural networks versus, let's say, a deep learning network or CNN is that the hidden layers actually are recurrent in the sense that the data that's actually normally fed out to the next layer is actually not fed to another layer in space, but actually fed back to the same neurons, or there's a feedback loop back to the same neurons. So these hidden layers that we have are actually recurrent in terms of time, right? They are actually being reused over and over again in time. So this type of networks are actually deep, not in terms of the space that they occupy. It means there are many layers in space, but they're actually very deep in terms of having many layers stretched out over a time period, right? So they are able to keep track of very long sentences. For example, if you have a long time sequence, the recurrent neural network is able to keep track of it if you allow it to recirculate many iterations within these hidden states. So another way to think about it is that recurrent neural, this is what I mentioned, RNN are recurrent because they perform the same task for every element of the sequence, right? The information is fed back to itself, with the output being dependent. The output here is dependent on the previous input that's fed back to it. Another way to think about this is that actually RNN, they have a form of memory. They can remember what was the appearance of the data before this in the previous iteration and the previous iterations before that as well. So they have a kind of memory of what has happened before. So let's take a look at the RNN structure in more detail. So we have the input here, X, and we have the output O. And there's a series of weights taking you from the input X to the hidden layer states, or S. Okay, so S represents the hidden layer states. It could be a number of neurons instead of just one. And the output is basically connected through weights from the hidden states, S, to the final output neuron through the weighted matrix V. Now, there is a feedback loop, right? So as I mentioned before, the data that's actually being passed out of the hidden states is actually fed back and reused for the hidden states in the next iteration. Okay, so there's actually this feedback loop that goes back into from the output back into the input. So if you were to unroll or unfold this neural network in time, so let's say the first unit of time, at time t minus 1, x will have the input xt minus 1. It will be fed in through u. So there will be some initial hidden state that's actually fed to this hidden state t minus 1, and this hidden state t minus 1 generates the output t at t minus 1. Now the t minus 2 input is actually fed into this hidden state through the weighted matrix W. Now at the next instance of time, at time t itself, you find that xt is again fed to the hidden as an input through u to the state st, but st minus 1, the state in the previous time instance actually fed through the matrix W to the state at this present instance, or t. And again, passing through V matrix that you get output here. And for the next time sequence, you have where it's x is equal to t plus 1, you have the same U matrix, and then again, t is fed into t plus 1 via the matrix W. And this continues on to t plus 2, t plus 3, until as long as you need to remember how many words you need in this sequence, that's basically as deep as it needs to go. So it's quite computationally intensive because you need to repeat each of these matrices and do the training for every instance in time. So if you have just three words like grandma bites dog, you just need three hidden sequence of hidden states to remember these three words, right? But imagine you have actually a whole book, right, or encyclopedia. So you have thousands of words in there. Your sequence that you need to remember potentially may be very long. Okay, it's definitely longer than just three notes. So as I mentioned before, if you look at the so-called layers in terms of time, right, the number of iterations you need, it can be very deep, okay, because of the time sequence in the hidden states. But in terms of the space that's occupied, actually the hidden states is just being repeated. So it's actually just one single structure being reused over and over again at different instances of time. So just to repeat again, each of these quantities S, X, and O, they are not just one single value. They could be a vector of values. So xt is actually the input at time t of all these various of this vector x, and is passed through a matrix to actually affect the vector of hidden states, okay, or called st. Now, st itself is the hidden state at time t, so it's actually a memory of the network. Is calculated based on the previous hidden state after passing through W, and it's also affected by the present input. Now, these two in combination through the hidden states is actually forwarded to the output state itself. Okay, so there are different configurations. Sometimes O1, OT minus 1, OT as well as OT plus 1 are actually important. But if you only want one output at the end, for example, whether this outcome is good or bad, right, given these three words that are actually input to it, then you can just take one of the output at the final instance of time of OT plus 1. Now, the output itself will be passed through some sort of activation function as usual, right? There's actually the structure of this neural network is the same as what we will normally get in any neural network. So after the linear combination of the weights with the input values from the previous state and the input values weighted sum of the inputs values, there is some sort of activation function that's actually applied to the weighted sum of these two. So st is some function of uxt plus wst minus 1, right? And this activation function could be actually a non-linear function like a ReLU function or a hyperbolic tangent. Now the final output OT is you may apply with some sort of simple classified network, like what we mentioned before, fully connected network, and we can apply a softmax function to the final output. So this last part here, just like in the CNN, could be a normal neural network that actually combines the output that's from the hidden state. So these hidden states actually, after a few iterations, they represent the extracted features or the extracted key information from the input data itself, right? All X. So you recognize something about the input data. So if the sentence that you're trying to recognize was grandma bites dog, that hidden state basically remembers that this word grandma was occurring in there and bites was occurring there and the dog was occurring there as well. And finally, so it remembers those three. And if I want to see these three sequence of words, my output will basically be maximized when I see all these three words present in the previous input data.